Hello and welcome everybody to this new edition of the ICTS String seminars. Today it's a pleasure to have Harvey Reall talking about the second law of black hole mechanics in effective field theory. Harvey is happy to take questions during the talk, so to some reasonable extent, feel free to interrupt him whenever you have a question. The floor is all yours, Harvey. We're looking
Thank you for the invitation to speak. So I'm going to tell you about work that I did last year, mainly about work I did in this paper with Stefan Hollands and Aron Kovacs. But I'll also say a little bit about a paper I had a few weeks ago with my student, Iain Davies, which follows up some of the ideas in this first paper. So I'm going to be talking about black hole mechanics, so let me say a few words about the usual laws of black hole mechanics in general relativity, where we have GR coupled to matter fields obeying suitable energy conditions. So the first law of black hole mechanics tells us about linear perturbations of a stationary black hole, a time-independent black hole. So it says if we perturb a stationary black hole, then the perturbed black hole satisfies this equation where dm is the change in the mass, ds is the change in the entropy. The entropy is given by the Bekenstein-Hawking formula in terms of the area, as usual. T is the black hole temperature, given in terms of the surface gravity by Hawking's formula. dj is the change in the angular momentum, and omega is the angular velocity of the black hole. So that's the first law. And then in standard GR, of course, the second law is the famous Hawking area theorem, which says that the area is an increasing function for a dynamical black hole, which therefore translates into the statement that the entropy is increasing or non-decreasing. And so the classical area law becomes the second law of thermodynamics for a black hole. So that's for standard GR. But about 30 years ago, Wald showed that the first law of black hole mechanics actually holds much more widely. It can be proved for any theory of gravity arising from a diffeomorphism invariant Lagrangian. So of course, that kind of theory typically contains terms with higher than second derivatives. So this is a first law that holds for a large class of higher derivative theories of gravity. So in particular, because he proves a first law, he has to present a definition of entropy that holds for such black holes. And so Wald's work gives a definition of black hole entropy for this class of theories, at least for stationary black holes, in other words, time-independent black holes. And that is the famous Wald entropy. So in this talk, I'm going to be talking about the second law and whether one can also obtain a second law for this class of theories. So, of course, there's been work on this in the past. And so Iyer-Wald, shortly after Wald's original work, made a proposal for a definition of black hole entropy in this kind of theory. So any theory arising from a diffeomorphism invariant Lagrangian. So it's a little bit technical, and I don't really have time to explain their proposal in detail, but let me just give you an example of what it looks like. Let's look at Einstein-Gauss-Bonnet theory. So the Lagrangian here is just the usual Einstein-Hilbert term plus a cosmological constant. And then you add this Gauss-Bonnet term to the action. The Gauss-Bonnet term, if you've not seen it before, is this particular combination of terms quadratic in curvature. This term is topological in 4 dimensions, but not in higher dimensions. So this is a particular 4 derivative term that you can add to the Einstein-Hilbert action. And for this theory, the Iyer-Wald entropy of a cross-section of the event horizon, C, is given by this formula here. It involves the intrinsic Ricci scalar of the horizon cross-section. So that's just an example of what it looks like for this theory. So if I return to the general discussion of this, then the Iyer-Wald entropy has various nice properties. So it's free of various ambiguities. that's present in the covariant phase space formalism that this is based on. It agrees with the Wald entropy for a stationary black hole, and it satisfies the first law. But Iyer-Wald left open the question of whether it satisfies a second law, in other words, whether it's increasing under a dynamical process. A little later, there was work by Jacobson, Kang, and Myers, who looked at a special class of theories, the so-called F of R theories. These are theories where the Lagrangian is just a function of the Ricci scalar. And they showed, they managed to prove a second law for this class of theories. And they commented on the fact that their entropy, which is basically the derivative of this function, it actually differs from the Iyer-Wald entropy. And so perhaps that's evidence that the Iyer-Wald entropy probably does not satisfy a second law in general. Okay, so in this talk, I'm not going to be trying to discuss a second law in full generality, but we're going to restrict to a perturbative setting where we just look at perturbations around a stationary black hole solution. So I'll assume the metric is something like this. It's there's some stationary black hole metric, G bar, and then we've got some first order metric perturbation, some second order metric perturbation, and so on. And the physical situation that we have in mind here is the process of a black hole which is relaxing down to equilibrium. So it may have done something dynamical in the past. There may have been a black hole merger, for example, but we're only looking at the very late stage of the evolution as the black hole settles down to equilibrium. And if one is interested in high derivative terms in the sense of effective field theory, as we shall be, then this perturbative setting seems to be the optimal situation in which higher derivatives might play an important role in the second law. And the reason for that is that if you have a highly dynamical situation, then the Bekenstein-Hawking term, which is always going to be present, is going to increase very rapidly, and that's likely just to overwhelm any contribution from any higher derivative terms. And so you need to focus on a situation where that Bekenstein-Hawking term is not doing anything very dramatic, in order to see higher derivative terms having an interesting effect on the entropy. Okay, so that I've told you about what happened in the 1990s. Let's now come to more recent work. So a few years ago, Aron-Wall made some progress on this problem. So he described a procedure for defining an entropy which satisfies a second law to linear order in perturbations around a stationary black hole for any diffeomorphism invariant theory. So Wall's procedure adds certain terms to the Iyer-Wald entropy, and so it's Iyer-Wald plus some new stuff, and so therefore we decided to call it the Iyer-Wald-Wall entropy. So this is the thing that Wall's procedure produces. So this defines an entropy to linear order in this perturbative situation that I've just described, and it's for any diffeomorphism invariant theory. So the simplest kind of terms that this procedure generates schematically look like this. They're of the form KK bar, where K and K bar are a pair of matrices that are going to play an important role in this talk. These are the matrices that describe the expansion and the shear of the outgoing and ingoing null geodesics, which are orthogonal to a cross-section of the horizon. So in particular, the outgoing geodesics here are simply the generators of the horizon, the null geodesics that move along the horizon. So K here describes the expansion and the shear of the horizon generators. K bar describes the expansion and the shear of the geodesics which fall into the black hole from this horizon cut. So you can work out what these look like in particular examples. So the example I presented earlier, Einstein-Gauss-Bonnet, is somewhat atypical because these terms turn out to be absent for that particular theory. But in general, they will be present. And these are just the simplest kinds of wall terms. In general, you can get much more complicated terms. Now, as I said, this wall procedure produces an entropy which satisfies the second law to linear order. But to linear order, the second law is kind of boring. It simply says that the entropy doesn't change. So if S dot here is the rate of change of the entropy with respect to some time parameter along the horizon, then to linear order, the second law just says that delta S dot is 0. So delta here means the first variation around a stationary solution. And it's easy to understand why, because if delta S dot were positive, if you had an increase in entropy at linear order, then you could simply multiply the perturbation by -1 to reach delta S dot negative, which would violate the second law. And so therefore, to linear order, the second law just says that the entropy is constant. So if you really want to see an entropy increase, you have to go beyond linear order and work to quadratic order in perturbations around a stationary black hole, which is what we'll be doing. I should comment that there's another way around this, which is to add an external source. So Wall does this by coupling gravity to matter described by some external energy momentum tensor satisfying the null energy condition. And that then also gives you an entropy which increases. This is something you can get away with at linear level, but I don't think this approach is very attractive once you go beyond linear level. And if you're looking at higher derivatives, theories with higher derivatives, there's no reason, for example, why the matter should satisfy this null energy condition. So we won't be doing that. Okay, so let me give you some.
Can I ask a question, Harvey?
Yeah, please go ahead.
This Iyer-Wald-Wall entropy, does this also disagree with the Jacobson-Kang-Myers if you specify it to F of R theories?
No, I think it agrees to the order to which linear, if you only look at linear perturbations of a stationary black hole, they agree. Yeah.
I see. Iyer-Wald does not agree, but Iyer-Wald-Wall does agree.
Correct, yeah, because Iyer-Wald-Wall is adding stuff to Iyer-Wald. That's right. Yeah.
Okay,
I think
thanks.
that's true. Okay, so I just want to say a few words about a variational picture that we found helpful, although it's not essential for understanding what we've done. So let's assume that you have some theory which admits an entropy S satisfying the second law. Then if we look at a stationary black hole, then that will have S dot equal to 0 because the entropy is not changing because the black hole is time independent. And so if there is a second law, then this means that the stationary black hole actually minimizes S dot within the space of horizon cross sections, which I'm not going to attempt to define. But clearly S dot minimizes this inequality. And so it then follows that a necessary condition for the second law to hold is that perturbations of a stationary black hole must satisfy the conditions corresponding to minimizing S dot. In other words, the first variation should vanish and the second variation should be positive. As I've explained, the Iyer-Wald-Wall entropy satisfies this first condition, so it extremizes S dot, but there's no reason why it should satisfy this second condition. And so this extremum might simply be a saddle point of S dot rather than a true minimum. Okay, so that's another way of looking at this perturbatively. Okay, so let me come to what we've done. So the new thing that we've added, I think, to this story is to work to put everything within the context of effective field theory. So I'm going to spend a few slides explaining what we've done in this situation. So let's, for simplicity, just consider vacuum gravity. So we make some comments about matter fields in our paper, but let's just focus here on vacuum gravity. So in effective field theory, we would assume that the Lagrangian is the usual Einstein-Hilbert term and the cosmological constant. And then you add to this action, the Lagrangian, all possible high derivative terms, which we order according to how many derivatives they contain. So first we would add terms with 4 derivatives, and there are 3 possible terms we can add there. There's a term quadratic in the Ricci scalar, a term quadratic in the Ricci tensor, and then there's this Gauss-Bonnet term that I wrote down earlier, which includes the term quadratic in the Riemann tensor. And then there'll be, these are all terms with 4 derivatives in total. Then we'd have terms with 6 derivatives, 8 derivatives, and so on. And we're going to assume that the coefficients of a term with k derivatives have coupling constants which are proportional to appropriate powers of some length scale L, which we will refer to as a UV length scale. So this is the usual thing in effective field theory, where this is characteristic of the scale of the physics that is integrated out to obtain this effective field theory. So for example, in string theory, you get corrections like this, where L would be the string length. Viewing high derivative terms in the sense of effective field theory restricts the scope of the second law in 2 important ways that I'll now describe. So first thing is that when you look at theories with high derivatives, if we truncate this high derivative Lagrange into some order in derivatives, then we'll have a high derivative theory. And it's well known that solutions of high derivative theories can typically exhibit pathological behavior. So that there are solutions with runaways or rapid oscillations at the UV scale and so on. And these are all unphysical. An effective field theorist would say these lie outside the regime of validity of effective field theory. And so one new thing in our approach is that rather than trying to prove a second law that holds for all possible solutions of this theory, we're going to restrict the scope and only try to prove a second law for solutions which lie within the regime of validity of effective field theory. So more precisely what I mean by that is if we define capital L to be the smallest length or time scale over which the solution varies, then this could be, for example, the size of the black hole, or it could be some dynamical time scale associated perhaps to a quasi-normal mode or something like that. But the important thing is we assume that this length scale, time scale is large compared to our UV scale L, and that's just a standard EFT assumption. And so with this assumption that big L, little l over big L is small compared to 1, then terms with increasing numbers of derivatives are expected to be increasingly less important. One thing I would emphasize is that we do not assume anywhere that the dynamical black hole solutions that we're considering are constructed perturbatively by an expansion in little l over big L. And the reason for that is it's well known that if you have in a time dependent situation, if you do an expansion like this, it can lead to terms which grow in time. You see secular growth, and that these are just an artifact of performing the expansion. So it's easy to see, for example, just looking at quasi-normal frequencies, if you have a perturbative shift in a quasi-normal mode of this order, and then you expand the quasi-normal mode, you'll get things which grow linearly in time. And it's just an artifact of performing the expansion. So we're not going to do any kind of expansion of the solution in this parameter, but we are assuming that this is true, that we are within the regime of validity of effective field theory. So in practice, in effective field theory, we're not going to know the action to all orders, but only up to some number of derivatives. So let's say we know the terms in the Lagrangian up to and including n derivatives. We can then write the equation of motion like this, where on the left-hand side, E mu nu is just the standard GR things, plus the higher derivative corrections that we know, in other words, including the terms with up to n derivatives. And on the right-hand side, this is all the stuff we don't know, coming from terms with more than n derivatives. I've written it as order little l to the n, but on dimensional grounds, I should really write this little l to the n over big L to the n plus 2. I'm not going to do that. You can reinsert these factors of big L everywhere just by dimensional analysis. So I'm just going to write it like this. But anyway, this is coming from the higher order terms that we don't know. The left-hand side is the terms that we do know. So here's that equation again. So the second thing that we do is that's novel, I think, is that if we have equations of motion like this, we don't know the equation of motion exactly, but only modulo these higher order terms. And so since we don't know the equation of motion exactly, we shouldn't aim to prove a second law that holds exactly. And instead, the second law should only hold to the same order of accuracy as the theory itself. In other words, modulo possible higher order terms of this order. So the goal, therefore, is from the terms in the equation of motion that we know, we want to construct a black hole entropy S that satisfies a second law modulo terms of this possible size. In other words, we should have an equation like this. So S, we don't aim to prove that S dot is positive definite. It can be slightly negative, but the amount it could be negative is of the same order as the higher order terms in the equations of motion that we don't know. And in particular, by increasing n, increasing the number of derivatives that we know, increasing our knowledge of the effective field theory, then we decrease this term on the right-hand side, and therefore we increase the accuracy to which the second law is satisfied. So I think this is kind of the optimal thing one could expect to do in proving a second law in effective field theory. So what we do is we don't actually manage to do this in general, but what we have done is that we can do this perturbatively. So we've shown how to define a black hole entropy S that achieves this to quadratic order in perturbations around a stationary black hole. So this is quadratic order in the sense of this this amplitude expansion that I mentioned earlier. So quadratic order in the amplitude of perturbations around the stationary black hole. So the second variation of S dot around a stationary black hole is positive modulo possible terms of order little l to the big N. And we do this by taking the IWW entropy, the thing that Iyer-Wald-Wall gave us, and we add new terms of quadratic order to that entropy in order to achieve this. So in equilibrium, so let me say a few general things about our entropy. So in equilibrium, this entropy reduces to the Wald entropy, so that's good. And to linear order in perturbations around a stationary black hole, it agrees with the Iyer-Wald-Wall entropy, and therefore it satisfies the first law. So that's also good. Now, if we look at, if the terms in the equation of motion that we know contain up to n derivatives, then our procedure produces an entropy S containing up to n-2 derivatives. So it contains terms with up to n-2 derivatives. Now, the new terms that our procedure produces, in other words, the terms that we add on to the IWW entropy, always involve at least 4 derivatives. And so that means they only appear when n is at least 6. So for terms in the action with 6 or more derivatives. So in particular, if we just look at the leading order high derivative corrections to Einstein gravity, those are 4 derivative terms. So they have n equal to 4. And our terms are not present in that case. And so for the leading corrections to Einstein gravity, what our work shows is that the Iyer-Wald-Wall entropy without modification already satisfies the second law to quadratic order in this sense of effective field theory that I've just described. In other words, the second variation of S dot is positive modulo terms of the same size as those coming from the 6 derivative terms in the action that you don't know. So let me give you an example of how this works for a particular theory. So I discussed Einstein-Gauss-Bonnet earlier. Let's return to that example. So Einstein-Gauss-Bonnet is a theory where we have these 4 derivative terms in the action. Remember, this is quadratic in curvature. So what we can do with this theory is let's say So our procedure works for any effective field theory. We could take Einstein-Gauss-Bonnet theory. Let's say we view this as a very special kind of effective field theory for which, for some unknown reason, all of the higher order terms with 6 or 8 or so on derivatives all just have coefficients which happen to be exactly 0. Okay, that from an effective field theory perspective, that's very unnatural. But we're from our perspective of producing an entropy for this theory, that's perfectly fine. We can work with that. So let's work with that here and see how we produce an entropy. So let's say we have this theory and we trust it up to 2 derivatives. In other words, we just have the Einstein-Hilbert term and the cosmological constant. So then the entropy density, I can write that as S over 4G. Then if we're up to 2 derivatives, we know the entropy, it's just Bekenstein-Hawking, which corresponds to S equal to 1. Okay, and this will satisfy a second law modulo the fact that we have these higher order terms which we've not taken account of. And so in this theory, the Bekenstein-Hawking entropy will satisfy the second law modulo terms of order L squared. Okay, but now we can go one step further and we can now include this term. Let's say we now trust this theory up to 4 derivatives. Okay, so now we can we have the IWW entropy, and I've just told you that up to 4 derivatives, this already satisfies the second law to quadratic order modulo terms of L to the 4th. Okay, so this entropy now, our work shows, will satisfy the second law to better accuracy than this entropy. So this entropy, the Bekenstein-Hawking, only satisfies the second law modulo L squared. We've now got an entropy which satisfies the second law modulo L to the 4th. But now we can keep going. Let's say we now trust this theory up to 6 derivatives. In other words, the coefficient of the 6 derivative terms here really are 0. So in our recent paper, we worked out then what the next term is in the entropy for this theory is. And schematically, it looks like this. There are terms of the form KK, K bar, K bar. Well, remember, K and K bar are these 2 matrices describing the expansion and the shear of the outgoing and the ingoing null geodesics, orthogonal to our horizon cross-section C. So this is schematic. There's an explicit formula in our paper that there are 9 different terms of this form that appear in this formula. But the point is that this now satisfies the second law to better accuracy than the previous formula did. This now satisfies a second law to quadratic order modulo terms of order L to the 6th, which is smaller. And in principle, you can use our procedure to keep going and generate an entropy which satisfies a second law to arbitrary order in the Gauss-Bonnet coupling L to quadratic order in amplitude. So that's roughly how it looks for this theory. There is an issue going beyond 6 derivatives, which I'll come back to a bit later. Okay, so if there are any more questions, this will be a good point to ask them, because I'm about to give you a little bit more of the technical details in what we do. Okay, I shall continue. So our work is based on, as with Iyer-Wald-Wall's work, it's based on using a particular class of coordinates for the black hole. So these are the well-known Gaussian null coordinates. Let me just recap how they are defined. So we assume we have some black hole spacetime with a smooth horizon that is settling down to equilibrium at late time. So at late time, we're approaching a stationary black hole solution. So Gaussian null coordinates are defined as in this picture. So this line here is the event horizon. And if we pick a cross-section of the horizon, this heavy dot here, then we can introduce coordinates xa on that horizon cross-section. And we then let V be the affine parameter along the null geodesic generators of the horizon measured from this cross-section. So we've now defined coordinates V and XA on the horizon. And now if we pick an arbitrary point on the horizon, we consider null geodesics transverse to the horizon. So we shoot them off in a particular direction, and we let R be the affine parameter along those geodesics. And so that now defines a nice coordinate system locally near the horizon, VRXA, where r equal to 0 corresponds to the location of the horizon, and v is a time coordinate along the horizon. It's the coordinate, the affine parameter along the generators of the horizon. So in these coordinates, the metric looks like this. So it involves three unknown functions. So there's this alpha here in the VV component of the metric. There's this beta in the Vx component of the metric. And there's this mu. Mu here is just the induced metric on a surface of constant V and R inside the horizon. So there's an important kind of scaling symmetry of this class of metrics, which is called a boost. So if we rescale V by multiplying by some constant A, and we rescale R by dividing by the same constant, then this leaves the form of the metric invariant. And we say that a quantity has boost weight B if it picks up a factor of A to the power B when we do this kind of rescaling. So in particular, alpha, beta, and mu all have boost weight 0, which I hope is fairly clear from the metric, just from the ways the V's and the R's appear. Whenever you see a V in the metric, there's an R balancing it. So alpha, beta, and mu are all boost weight 0. But if we look at the quantity K, which I've referred to several times, let me now define it. It's just the V derivative of mu with a factor of a half. So this describes the expansion and the shear of the horizon generators. This is a quantity of boost weight +1. And if you look at the expansion and shear of geodesics transverse to the horizon in this direction, this is given by the R derivative of mu. This is the quantity I've called K bar. These have boost weight -1. So an important property of stationary black holes, so time-independent black holes, is that if we assume the 0th law of black hole mechanics is true, so this says that the surface gravity is constant on the horizon. If this is true, then one can show that all positive boost weight quantities vanish on the event horizon. And this is very important in what Iyer-Wald did and in what we'll be discussing. Okay, so let me just briefly remind you of how the usual proof of the second law works in standard GR. So in GR, if you look at the rate of increase of the horizon area is given by, in terms of this K I've defined here, it's given by the integral of the expansion of the horizon generators. So mu here, remember, is the metric induced on the horizon cross-section. K with its indices contracted is the expansion of the generators. And so you integrate that, it gives you the rate of increase of horizon area. So to prove the second law, one uses Rayleigh-Jury's equation, which I've written out here. This is basically the VV component of the, it's a formula for the VV component of the Ricci tensor. So if we know something about the sign of the Ricci tensor of this component, let's assume we do. Assume what's called the null convergence condition, that it says that RVV is non-negative. Then you can see the right-hand side is then non-negative. Sorry, the right-hand side is then non-positive. Both terms are negative. And so the V derivative of K is therefore decreasing. Now, our assumption that things are settling down to equilibrium at late time implies that K is tending to 0 as V tends to infinity. And so if we have something decreasing, which is tending to 0, then that thing must be positive or non-negative. And so we've deduced that K is positive, and therefore the area is increasing. So, okay, to do that, we assume this null convergence condition. If we have the Einstein equation coupled to matter, then this is equivalent to the null energy condition satisfied by matter. So that's the usual proof in standard GR. But of course, when we include higher derivative terms, we don't actually know anything about the sign of RVV. There's no reason why this should still be true. So if we're looking at this effective field theory I've been discussing, all we know is that RVV is equal to some 4 derivative thing, which is of order L squared, but we don't know anything about its sign. And so this important condition is no longer true, and so we don't have a second law anymore. Now, what you might say is that, well, if we're working in this setting of effective field theory, surely we'd expect this 2 derivative term coming from standard GR to dominate this stuff coming from higher derivatives. And that may well be true in general, but there are certainly situations where it's not true. So one situation is if you're looking at linear perturbations of a stationary black hole. So the reason is that K vanishes for a stationary black hole. So this is of quadratic order. So if you're looking at linear perturbations, that's negligible, and this will be the dominant term. And that's basically the problem that the Wall procedure is designed to fix up. If you go beyond linear order to quadratic order, as we shall, then this is now definitely there, but there may be situations where this term just happens to be small somewhere on the horizon. And also there's no reason why, a priori, why this kind of term should dominate some of the possible higher derivative terms coming from RVV. So there are things like this, for example, involving this, the V derivative of this quantity beta in the metric. There's no reason a priori why this gives us any control over this, or even over this, where this is a spatial derivative of K. If it could happen that K is small somewhere, but its spatial derivative is not small, in which case this would not dominate this. And so the validity of effective field theory doesn't guarantee that the right-hand side has a good sign. We need to find a way of controlling that. We work with an entropy current. So an entropy current is a vector field defined tangentially to the event horizon. So it has components SV, SA in our Gaussian null coordinates. SV is just the entropy density on the horizon. So for example, in standard GR, the entropy current just has components 1, 0. The entropy density is 1 in our units. And then the entropy of a horizon cross-section, a cross-section of constant V of our horizon, is just given by integrating SV over the horizon, over that cross-section, like this formula here. We define the divergence of the entropy current like this. So this mu, remember, is the induced metric on a cross-section of the horizon. So there's some V derivative here of the entropy density. And this D here is the covariant derivative defined by our metric, this mu here. So this is a divergence in the spatial directions of the horizon. Again, in standard GR, this SA is just 0, and this just reduces to the trace of K, which is just the expansion of the horizon generators. So if we try and copy the kind of the argument we use in standard GR, we would take the time derivative of the entropy, take the time derivative of this, so we get the V derivative of this integrand, and then we can trade that for the divergence of the entropy current, because this term here is just a total derivative, and so it integrates to 0. So we've related S dot to the integral of the divergence of the entropy current. So if we try to copy the usual GR strategy, our next step would be to try and show that this divergence is a decreasing quantity. And then because if we assume late time equilibrium, this quantity will tend to 0 at late time. If it's decreasing and tends to 0, then it must be positive, and then we get an increasing entropy. But unfortunately, this doesn't work. So we have to do something a bit different. So to explain what we do, let me, I'll first tell you that the Wall's approach can be formulated in terms of the entropy current I've just introduced. And in fact, the reason I've introduced it is precisely because Wall's approach is most elegantly expressed using that. So in particular, you can show that if the equation of motion is E mu nu equal to 0, here I'm stepping away from effective field theory for the moment because Wall's approach doesn't require us to use the effective field theory framework. So if the equation of motion of some high derivative theory is this, then what this entropy current approach shows is that the time derivative of the divergence of the entropy current is related to the VV component of the equation of motion, plus terms of quadratic or higher order in these positive boost weight quantities. Now, remember, these are quantities which vanish for a stationary black hole. So these are also of quadratic or higher order when we consider perturbations around a stationary black hole. So in Wall's approach, these don't matter. And in fact, because we're looking just at the VV component of the equations of motion, this is some kind of generalization of Ray-Choudhury's equation. And in particular, this F here, which is of quadratic or higher order, contains the usual quadratic term in Ray-Choudhury's equation that we're familiar with from standard GR, this KK term. Okay, so, but this also contains all sorts of high derivative junk that we don't have much control of a priori. So basically what we do is we show that this F can be rearranged in a nice way at the expense of these assumptions I mentioned earlier. Well, one is that we're going to be invoking effective field theory. The second thing we have to do is we have to go on shell. So this equation up here is an off-shell identity, but in our approach, we have to go on shell. We have to use equations of motion in order to rearrange this F in a nice way. So what we show is that if we assume the effective field theory equation of motion is known up to n derivatives, as I explained earlier, so here on the left, these are the terms we know with up to n derivatives. On the right, this is the stuff we don't know with more than n derivatives. Then what we show is that working order by order in derivatives and using the equations of motion, we can add new terms to the IWW entropy density to define an improved entropy density, I'll call capital S, with an associated entropy current, which satisfies this equation here. So it says the time derivative of the divergence of the entropy current is equal to the square of something, where this square involves the matrix K I introduced earlier, but also this quantity X, which comes from the higher derivative terms. So there's some matrix X, which we add to K, and it arises in this nice way. It's a positive definite or negative definite term on the right-hand side. But we also have this other term here, which is a divergence of another quantity Y, again arising from the higher derivative terms. This is what we have on the right-hand side. On the left-hand side, the new stuff we have to add to the entropy density is quadratic in positive boost weight quantities. And importantly, this Y is also quadratic in positive boost weight quantities. And the final thing is that we're working within this framework of effective field theory. So there are also possible terms order L to the N on the right-hand side of this equation. So these are terms of the same order as the unknown terms on the right-hand side of our equation of motion. And as I explained earlier, that's always what one would expect in effective field theory. So as an example of where we use equations of motion, I mentioned earlier that you could have terms like this arising in the analog of Ray-Choudhury's equation. A priori, one has no control over this kind of term. However, we can use an identity for the VA component of the Ricci tensor, which involves precisely this V derivative of beta. And there's other stuff here, but that other stuff is all stuff that we can control. And so the strategy is to eliminate things like this by trading them for Ricci components, and then eliminating those Ricci components using equations of motion. So that's where the on-shellness of this procedure comes in. Okay. Okay, so here's our master equation again. So how do we use this equation? So again, if we assume late time equilibrium, then this thing on the left-hand side, the divergence of the entropy current tends to 0 as V goes to infinity. And so if we integrate this equation from V0 to infinity along a horizon generator, then we get an equation for the divergence of S at time V0 in terms of the integral of the right-hand side with respect to V. Now, if we were just following the usual GR strategy, we'd say this thing is positive, and we'd like to argue that the whole thing is positive on the right-hand side, but actually this term isn't positive, and we have no control over the sign of this. And so we need to do another step, which is now to integrate this equation over the horizon cross-section. Now, if we integrate this over the horizon cross-section, I explained earlier, this is exactly what we would call the rate of increase of entropy. So the rate of increase of entropy is the integral of this. So substituting this formula into S dot, we get this big formula here. And now we're almost done. We've now got an integral with respect to V and with respect to X. So we're integrating over the whole horizon to the future of our cut. the cut of constant v. And what we would like to say is that this term here is a total derivative. And so when we do the integral over the horizon cut, it drops out. But the problem here is that we're doing an integral over v as well. So this derivative refers to the metric on a horizon cross-section at a range of different times, not just the time v0 that we're integrating over here. However, so we can't just interchange the orders of integration here. However, I told you earlier, this y is of quadratic order in perturbations because it's a quadratic in positive boost weight quantities. And so that means that if we're only working to quadratic order, we can evaluate this covariant derivative with respect to the stationary background geometry, and then we can interchange these two integrations, and this total derivative then does drop out. And so if we're only working to quadratic order, then indeed this term drops out, and we're just left with this positive definite thing on the right-hand side. And so we obtain a second law to quadratic order modulo these terms coming from the unknown higher derivative effects, or modulo terms of the same order as the unknown terms in the equations of motion. So we've achieved what we set out to prove the second law holding to quadratic order in perturbations around a stationary black hole in this EFT sense that I described earlier on in this talk. Okay, so that was all a bit technical, so I'll get less technical now. So here's our equation again. We have a second law which holds to quadratic order in perturbations around a stationary black hole in this EFT sense. So modulo terms as the same size as the unknown terms in our equations of motion. So this holds for vacuum gravity. With matter fields, we haven't worked out the details in general, but the basic idea is that if you have an effective field theory containing matter fields, then as long as the two derivative terms in the action satisfy the null energy condition, then you can hope that you can play this completing the square game again, but now you'll get extra terms on the right-hand side where you also have to complete the square on the matter fields. And so we showed this works out for the simplest kind of matter field, which is just a scalar field. So it all works out for the effective field theory of gravity coupled to a scalar field. And I expect it would also work out, for example, for a Maxwell field. So we expect it to hold for a wide class of interesting effective field theories. Okay, so let me come to some issues with this, or questions about this approach. So one is gauge invariance. So if you're paying close attention, you'll have noticed that the second law that we've proved, and this is the same for Aron-Wall's approach, is it's a second law that holds for constant v cuts of the horizon. Okay, but in standard GR, that's not what we do. We don't fix a coordinate system and only look at constant v cuts. We look at arbitrary cuts of the horizon. And we'd like to relate the entropy of a cut C to the entropy of a cut C primed, where C primed is to the future of C. So how can we do that using this approach? So the idea is, well, we can always choose C to be at V equal to 0. So we can base our Gaussian null coordinates on this cut C. And then we can use some freedom that's present in the construction of Gaussian null coordinates, which is the freedom to rescale the affine parameter along each generator in a different way. In other words, you can perform a rescaling of V, which depends on X. So if you do that, you can make C primed also into a cut of constant V. And then we can use what we've just discussed, the second law that I've just described, to deduce that the entropy of C primed is greater than or equal to the entropy of C, at least to quadratic order in this sense of effective field theory. So that looks like what we want to do, but what we need to check is that our definition of entropy is gauge invariant when we do this rescaling. Because if it's not, then what we've done is we've defined the entropy of C in a way that depends on C primed, which is not very satisfactory. Okay, so we want to show that our definition of entropy is invariant under X-dependent rescalings of affine parameter. And I should say, this is not, as I said, this is not just an issue with our approach, it's also an issue with the Aron-Wall's approach. So this gauge invariance is not obvious even for the Iyer-Wald-Wall entropy, although it is obvious for Iyer-Wald, as they pointed out. So anyway, in our paper, we did manage to prove that the Iyer-Wald-Wall entropy is indeed gauge invariant under this kind of rescaling of the affine parameter along the horizon generators. Now, earlier on, I told you that for n equal to 4, so for theories with up to 4 derivatives, our entropy agrees with the Iyer-Wald-Wall entropy. And so for theories with up to 4 derivatives, our entropy is also gauge invariant. But what about more than 4 derivatives? Well, so this comes to the recent work with Iain Davies. So if we just look at vacuum gravity, then one way of investigating this problem is to just write down all possible terms that could appear in the entropy. And it's fairly easy to do that. So you can classify possible terms which could appear. And from that classification, you can immediately see that the gauge invariant terms can't occur for n less than 8. Okay, so if you're only interested in theories with up to 6 derivatives in the action, then everything is gauge invariant. And n equal to 8 derivative terms is the first place where gauge non-invariant terms could be generated by our procedure. And so do they appear? And so we had to do a calculation to investigate this. And so this involved some fairly heroic computer algebra work by my student Iain Davies. And he's confirmed that gauge non-invariant terms do indeed appear at 8 derivatives. So if you push things to 8 derivatives, this quite high order in effective field theory, then our entropy does generate gauge non-invariant terms. And so I think once you get to that level of derivatives, it's not entirely satisfactory. But I emphasize that if we're only looking at theories with 4 or 6 derivatives, in other words, the leading order EFT corrections to GR or the next to leading order corrections to GR, then everything is fine. Another issue concerns field redefinitions and uniqueness. So our definition of entropy appears not to be invariant under effective field theory field redefinitions. So for example, if we just take, let's just take standard vacuum gravity with just the usual Einstein equation in vacuum, R mu nu equal to 0. Let's perform a field redefinition in which looks like this. So we shift the metric by a term proportional to R mu nu and a term proportional to R times the metric with arbitrary coefficients C1 and C2. Notice this is trivial on shell. So on shell, R mu nu vanishes. And this is important because we want to compare the horizon before and after the field redefinition. And of course, the definition of the horizon depends on the metric. So if we change the metric, we would change the location. But since this is trivial on shell, we don't have to worry about that issue. But even though it's trivial on shell, it's well known this generates these 4 derivative terms in the action. And if you look at the associated terms in the entropy coming from these terms, these new terms in the entropy don't vanish on shell at quadratic order. So in other words, calculating doing the field redefinition and then determining the resulting entropy does not commute with substituting the field redefinition into the original entropy. Okay, so in other words, it changes the entropy. So the question is this a problem? And it seems to be, it's possibly related to things that have come up fairly recently in fluid mechanics. So relating to the uniqueness of entropy in a non-equilibrium situation. So in fluid dynamics, for example, if you look at a relativistic viscous fluid, then it's been shown that there are multi-parameter families of entropy currents which satisfy second law. So the entropy current is not unique, even in fluid dynamics. And so this seems that this is possibly the same phenomenon arising in gravity, that field redefinitions are just mapping between different possible definitions of black hole entropy, all of which satisfy a second law. in which case I don't think this is really an issue. Okay, so to conclude, so we have introduced a procedure for defining black hole entropy such that the second law is satisfied to quadratic order in perturbations around a stationary black hole in the sense of effective field theory. So there are various things that can be done in future work. So one thing we started doing with Ian Davies was working out what this entropy looks like for some particular kinds of higher derivative theories. As I mentioned earlier, the calculations involved are very lengthy, and so one really needs to do all of this with computer algebra. So we used a package called Cadabra, which is very good for this kind of thing. Matter fields, so only the simplest kinds of matter fields have really been discussed in this context. So the scalar field, so working this out for other kinds of matter would be interesting. So I mentioned this issue of gauge invariance. So we've seen that once you get to 8 derivatives, you encounter this issue of gauge non-invariant terms appearing. So what one natural question is whether perhaps you could use gauge invariance as a selection rule on possible terms which could be present in the effective field theory. In other words, can you constrain effective field theories by the requirement that our procedure produces a gauge invariant entropy? I'm not too optimistic about that, just because the number of possible gauge non-invariant terms that can be generated is quite large, and it seems unlikely that by playing with the coefficients of the effective field theory, you can get all the gauge non-invariant stuff to cancel out, except in very special cases like F of R theories. But in any case, I emphasize the gauge non-invariance only appears when you go to quite a high order in derivatives, and if you're working only at the leading order or the next to leading order corrections to a 2 derivative theory, this is not an issue. There are a lot of our approach is reminiscent with the fluid gravity correspondence, so it might be interesting to explore those connections a bit. And of course, perhaps the main question is, all of this only holds to quadratic order in perturbations around a stationary black hole, and so clearly it's desirable to go beyond that and ideally get some result which holds non-perturbatively. But at the moment, that seems very ambitious, and we don't really have any good ideas for how to do that. Okay, so thank you for your attention.
Thank you very much, Harvey. Some of us on campus dropped out of the call because of a power outage for about 10 or 15 minutes, but I see that the other audience outside campus seem to have been able to follow. Are there any questions for Harvey? Feel free to unmute yourselves and ask. I see nobody with questions. Sorry about the mess in the middle. Thank you very much for your time and your talk, Harvey.
Okay, no problem. Thank you. How